Alright, so today we're actually going to talk about the core of microcontroller programming, interrupt service routines. It's a very important mechanism. So hardware events actually trigger interrupt service routines, very important. So what you see here, you can find it in the datasheet, is a table of all kinds of, well, if you look at the source, you see here all kinds of hardware events that can trigger. And what happens is really that at these addresses in your program memory, so the first address is all zeros, then you have address 2, 4, 6, you also have address 1 and 3 and so on. But at this particular address, if the hardware event called reset is happening, there's an interrupt service, there's an interrupt controller who detects that and will interrupt all the computation that you're doing and will look at this address to find out what is stored here. And what is stored there is a byte, and at address 0001 is a second byte. Together they form 16 bits, and that's the location where the interrupt service routine is written by you to then execute. So what we're having here is, if you want to write a interrupt service routine, because not for all these events you want to do so, you will actually create a mask bit of that interrupt. So you set that mask bit, we will come to that in a moment. But if you do so, in one of those control registers, you set that bit, that interrupt enable bit, then you must write the corresponding ISR because the compiler expects you to have such an interrupt service routine ready. So the table here contains the address, as I said, of the interrupt service routine that you're going to execute. For example, we are going to dive into this particular one, the USART RX. And if the receive buffer is full, then it will create a hardware event, and it is triggering this interrupt controller, right? And that will make it look at this particular address, and it will see, for example, the address 0xabcd. It will jump to ABCD in the memory, and that's where it will find the code for your interrupt service routine. So that's essentially what's going on, but it's kind of interesting to see this whole table and all the different kinds of interrupts that can potentially happen. So that's how a program will know or where to jump to when an interrupt service routine is happening. So we will be talking about program layout. So very important is that we have an initialization procedure. That's what we always start with. And we effectively set up all kinds of things. All kinds of registers that you want to set up. We will talk later about timers in 2 lectures, I believe. We talk about timers. We do all kinds of bookkeeping. And once we've done all of that, we're going to enable the interrupts for which we have written interrupt service routines. We do that by turning on a master interrupt bit. And that's depicted in the data sheet as this particular register. So there's an SREG register, and on the ith position, if you set this particular bit, that corresponds to the 7th position, then you will actually enable all the interrupts for which you have created an interrupt service routine. And there's a C macro called SEI, which we will be using to do this, rather than writing it ourselves. We could do that as well, but there's already a macro defined for setting up the interrupt service routines, to initialize those, I mean. So that's the global interrupt enable. Now, when we talk about program layout, the idea is that the main program gets into this while loop. And it's always like this. It's while 1, in other words, forever execute that same bunch of code lines on and on and on. And it happens at the background forever. And you never exit the main from the MCU really, right? It always is being called. And but interrupt-driven tasks can now be asynchronously called from main. So here's an example. take for example a hardware timer. And a hardware timer that you have in your MCU, we've been talking about this in this blog, timer 0, timer 1, timer 2, they actually clock at a certain speed, and they all have their own register with a counter, and that is being incremented. So what I can do is I can sort of program my hardware timer, we'll get to that at a later point. For example, that a hardware event is caused every 1,000 cycles, like every 1,000 times, say, that count is incrementing for that hardware counter. And when that happens, then a corresponding ISR can then be called. And what you could do, for example, suppose that these 1,000 cycles match 1 millisecond, you can have in that ISR like a global variable that is incrementing just by 1, and in that you can create your own software counter. Now we'll get to that in much more detail later on. But the beautiful thing is that you can have these interrupt-driven tasks, and so the idea is that upon reaching an a priori defined maximum value, then the background code calls a corresponding procedure, so that software counter may counting on its own for another 1,000 times, which is like 1 second, and then maybe the background code says, in the main says, if my counter reaches 1,000, then 1 second has passed, then do this particular task. It resets the software counter back to 0 and so on. Now, we'll get to this in much more gory details later on, because it's kind of interesting, but maybe also a little bit complex to really understand how that works. But right now, we're going to talk about the UART. Now here is first of all some remarks about interrupt service routines. They have no parameters, you don't give anything. There's no return value. They do save CPU state, right? Because your main program gets interrupted, you go somewhere else, you need to save the CPU state, you go somewhere else, you execute the code of the interrupt service routine, you jump back, and you load again the CPU state that you were at. And then you can just go forward with your main program as if nothing had happened in the meantime. So let's have here an example. So you have a bit value for position RxC0 in this 8th control register for the UART. Now if this one goes too high, when receiving a character, so that one goes too high when receiving a character is completed. Now what you could do is you could also create a mask bit in this Bth register for this particular position. The E here stands for enable, interrupt enable, and it's really talking about that if this goes too high, then, because if you would have enabled this, then an interrupt service routine associated to that hardware event will be called. So the interrupt is enabled for the flag when this particular register at this position goes from 0 to 1. If that happens, then the MCU will jump to the address of the interrupt service routine as indicated by that table that we just talked about. That's right at the start of your program memory, and it has a certain address. I think it's 0x0024. That's what I remember. Now when that interrupt service routine is called, it does take a little while before it gets there. It takes about 75 cycles to go in and out of an ISR. Why? Because you need to save the current state of the MCU, and there's still another bunch of overhead that you need to work with. Now, if you look at the architecture, what do we see here? So here we see the general computing unit, right? And first of all, you get your instructions from flash program memory. There's a program counter. The program counter is telling you where in this address space I am with my execution. So it indicates which particular instruction needs to be loaded into that register. It needs to be decoded by the hardware to what you exactly have to do. But the point is that we manipulate some general purpose registers, some computation may take place, and so on. There's also data that can be fetched. That's also very important. But this is the one that we're very interested in. So on the bus, we see a lot of other units, by the way, like a communication interface, SPI, some other kind of special timer, the analog comparator, some other stuff. But you see also here the interrupt unit, and the interrupt unit is independently in parallel checking what kind of flags are being set. When hardware events happen, like what we just talked about, like a character was received, then that particular flag in the UART control register A, right, will be set to high. That will trigger, that is noted by the interrupt unit, and when the interrupt unit sees that and also knows that the interrupt service routine should be called, then it will effectively interrupt all this computation. It first saves all this state, then it goes to the ISR instructions, those are executed, and then after that all this state that was saved is being reset back, and then the program goes on as before by moving forward the program counter to where we were in the main program, and we go forward. So that's what the layout is. Now if you're going once more in a different view, look at the actual memory, here it is, then we see here this interrupt vector table, and at 0x0024 we have something stored. Well, it's stored at 0x0024 and 0x0025, right? Because these are 2 bytes, AB and CD. So those are stored on 2 memory spots, 2 memory cells, and it contains an address. The address is somewhere over here, also in your program memory, and here you will see the ISR of your UART that you want to execute if a character is received. So that's pretty cool. So let's have a look at this this piece of explanation here. So say a character receive complete happens. What's going on? So the hardware event, which makes this particular flag non-zero, it goes to high, and then if this particular thing is enabled, the interrupt enable is set, a priori, you already did that, then the ISR UART RX is enabled. And that means that the interrupt unit sees that that flag was set, jumps to this particular address, sees this address, jumps to that address, and starts executing the ISR. That's the whole idea. So that's what we talk about here. Now, you cannot just immediately execute this, because you were somewhere with your instruction. Say, I'm here. Well, I first want to make sure that the corresponding instruction that is executing, which is the instruction that's right before that, is still executing. I want to finish that instruction. I'm not going to break in at that point. I wait till that instruction is finished. The program counter is pointing at where to fetch my next instruction, but that you will not do anymore, because you want to not jump to the next instruction, but you want to jump to the first instruction of your interrupt service routine. So what happens is that this program counter is saved for later use. We call that the program counter stack. It's pushed on top of it, and now the program counter becomes this particular value that it read from this address. You jump over here and you start executing. That's what's stated over here. The ISR is now executing. Up in return from the interrupt though, when you're finished here, you had the stack, you fetch this address, and now you know where to go in the main program, which is this particular location, where you find your next instruction, and that's what you're doing. So you get the next address, and you fetch this instruction, and you increment the program counter at the same time. So now you continue your execution in the main program. So that's how it works. So that's how an interrupt happens. So effectively, the interrupt unit scans all the flags in the table in a round-robin fashion. So it reacts very fast, right? and the execution of the main code is done at the same time by the ALU. There are two different hardware components, and so these two processes actually run in parallel. Alright, so let's talk about it once more, now in text, just for you guys to also read it over once more. It's pretty much what I just talked about, but let's do it once more. So there's some hardware event that sets a flag in some register. So for example, this guy, right? That's what we've been talking about. So it goes too high, and the corresponding interrupt is enabled. If that's the case, how do you do it? By initially programming this particular register to set the interrupt enable bit for the received character completed. Now, then the flag will be detected by the interrupt unit of the MCU, and that is possible because it scans this vector table in a round-robin fashion all the time. Now, the CPU is executing, what could be possible is that the CPU, if the CPU is executing already an ISR. I did not tell you about what can happen then. Well, then you first want to finish the ISR, else finish the current instruction. So either, the execution is already busy with an ISR. That can happen too. Then you want to finish the ISR first. That's what is done. And if you are just in one of the main instructions, then you finish that instruction. You push a program counter on the stack to remember where you have to jump back to when you want to continue the execution in the main program. And now you clear the I bit, so the I's position in SREG. Why? Because you do not want any other interrupts you do not want any other hardware events that can cause interrupts to interrupt your current interrupt service routine. You really do not want that. So that means that once that is done, none of the interrupts are enabled, and that means that you can really finish your ISR till the end. So that's what's going on here. The CPU jumps to the vector table, clears the corresponding flag, this one, and this particular guy. Then it jumps to the ISR indicated by the address in the vector table, like 0xabcd in our example. And then the compiler had created a binary which saves the state of your registers, the 32 registers, and now executes the ISR code that you have written for it. After that, restores that state, the 32 register that it had saved, go back, so that as if nothing had been done from the perspective of the main program, like everything is back and restored. And now you return from interrupt. And that actually enables the I bit in this particular register again. It means that all the interrupts are again enabled. There's a global enabling. Now you recheck the interrupt flag, so now it also rechecks the interrupt flag registers in the vector table, because maybe another hardware event may have occurred that created an interrupt, and that's what you need to check. Now what can be done? What kind of problems could we have here? Take for example an ISR which actually says print a statement. So if that's the case, you could do it, you could write an ISR, and in that ISR you say print something on your console. It turns out that that string that you want to print is being pushed to the print buffer. And that's a separate hardware module that is going to empty that buffer, and the program continues. So you go to the next instruction in your interrupt service routine, and at some point, very soon, the interrupt service routine is finished. But wait a minute. The hardware executes the printing statement parallel with the rest of the ISR, but the ISR finishes. So before the print statement is even finished, because the buffer is not yet emptied, the ISR may be triggered again. And if that's the case, it will immediately start issuing another print statement and overriding the buffer with something else. And this can happen so fast that nothing ever gets printed. And the funny thing is that you guys had seen that a little bit with not adding an F-flush statement after, I think the print statement before a scan statement earlier in one of the blocks. You saw some effects happening like this as well. But the cool thing is that an ISR, if you use it in the wrong way, can create similar problems. So it's good to note. So another one. In your ISR, you may enable the master interrupt bit. You could do that, but don't. That's really not a good idea, because then it will allow you to interrupt the interrupt service routine again, and that will create nested interrupts, and that's certainly not recommended. It's very hard to verify whether your code is actually doing the right thing. Now, if you don't do that, then the memory is only one event deep. So let's think about it. What does that mean? Well, suppose you're handling this particular flag. It went high, right? And then immediately when you enter the interrupt service routine, it's being pushed to low. But you finish the interrupt service routine, and maybe a hardware event happens, and that will set this again back to high. But your interrupt service routine is still executing, and then another hardware event happens. It was already high, and it maintains high. In other words, when you exit the ISR, during the execution of the ISR, a hardware event may have happened that set this again back to high, so that when you get out of the ISR, you will call it ISR again. But you will not call it twice. You will only call it once, because those two possible hardware events or more hardware events that have happened during the execution time of the ISR that can set this high, you cannot distinguish any of those. It is as if they all just happen just as one event. So you will avoid missing hardware events if your ISR code is computing for a very long time. So you do not want to execute an ISR code that takes a long amount of time. Generally, you just want to have one or two or a couple of instructions that just say a particular global variable to change to a certain value, and then in your main program you catch that happened, and you will do something with it. So it's very important to write efficient ISR code, and it's actually really important for writing good MCU code. And so then you will not miss hardware events per se, right? You can keep on accumulating those, and that really defines the reliability of your application. Alright, so how do I even know the name of the interrupt service routine that I need to write? So we decided that we want to write something for the USART for receive complete. There is this particular site at atmo.com, and it shows you a big table, and you look up, I want to write something for USART RX. I see my processor over here, and I need to write this particular interrupt service routine. So I need to program ISR USART RX fact. That's what I'm doing. So that's how you figure that out. So it's good to know. And let's have an example. So in this example, I'm going to explain to you how you can make the UART non-blocking. Remember, if we call fscanf, it's going to use the UART cat character. And in that UART cat character, we see this particular statement. It's a while loop that essentially says wait till this is set, meaning that a received character is complete, and then I can read it from my register, and I'm good to go. And then we have the echo over here, but let's just focus on these two lines.